This video is about the Keithley 502A, a milliometer that came to my attention recently. It's very similar to the HP 4328A, which is very commonly found, a bit more expensive and a very good instrument. I've used that before. A friend of mine has it, and this particular instrument is not seen much on YouTube actually. So I thought I would do a demo of it and going through some of the schematics and so on. If you're not too interested, you could skip to the end of this video where I show some measurements and actually performs quite well for an instrument that is almost probably in the order of 50 years old, I would say 45 to 50 years old, I'm not sure, but it's very simple in construction and using both tubes and transistors. So let's get into it. Here's a simplified block diagram of the Keithley 502A milliometer. Took me a little bit of effort to decipher the schematic which was in the manual, and this is basically a highly simplified version of that milliometer. So what we have is a completely different type of an instrument compared to a multimeter like or similar benchtop milliometer, which uses DC current and then measures the voltage that's developed across resistance. In this particular implementation, using an AC signal which is created by an oscillator over here that is sent into the resistance which is to be measured, the DUT, and the voltage is sensed as again an AC signal, and it's amplified by a transformer and then a set of gain stages, and then it's basically sensed, and then a current is sent through a meter that is responds to the in terms of resistance in a linear fashion. So the main reason this was done for was the application. The original intention was to measure with very low power certain devices which were sensitive for explosion and so on, such as squids and detonators and stuff like that, where you don't want to put in a large current which can actually cause that detonator to explode in the field and so on. So these are a lot of these instruments are battery operated as well, and the amount of power that they use is in the microwatts, and the voltages that are sent into the DUT are very small, as well as the currents that are sent in are very small. So there's another instrument in the same class as this one, that's the HP 4328A, which is a very well known instrument that you see frequently on eBay. It's much more expensive, and there are quite a few of those you see from time to time, but this one is pretty rare. I've never heard of this one until I saw one, and then I got one for fairly cheap, and so I tested it and it seems to be working. The only problem is that it's totally battery operated, so you need a lot of batteries, 9-volt cells and some mercury cells 1.35, but you can get away with using a 1.5 volt cell, but there are several types of batteries used, and this whole amplifier chain is built out of vacuum tubes, and these vacuum tubes are not the traditional large ones that you see in audio amplifiers, but these are sub-miniature types, very low power and fairly low voltage, like 20-30 volts on the plates. So it's extremely tiny, almost like a miniature bulb that you see in refrigerators and so on. But essentially this range is actually quite impressive, like 1 milliohm to 1 kilo ohm, just like this instrument, the 4328A, and it has the ability to have a restricted voltage mode or a low range mode, which can reduce the amount of voltage that is developed to around 20 millivolts, I believe, that can be used for certain applications, as I mentioned earlier. The normal mode actually uses a higher current, and so it's probably better for measuring larger, smaller resistances which may have a sensitivity issue. So to describe this again, there are 11 ranges over here, and depending on whether you're operating in a normal mode or the low normal voltage mode or the regular voltage mode, you can switch in that using the main switch. And there are 11 ranges here, and these are switchable again with a rotary switch. And basically there are 4 terminals, a Kelvin connection, and there are 4 leads actually, they are not joined together. And AC voltage that is developed across this duct is then, in the case it's done a low range mode, less than 3 ohms, there's a transformer that is in circuit. And if you're going in the higher resistance mode, you don't need a transformer, you just bypass it and AC coupled, and then this amplifier chain amplifies by around 120 dB by my estimation, because these amplifiers are fairly high gain GM, and times the plate resistance is around 2 mega ohms. So I would say each of these stages have a gain of around 30 or so, and so 30 raised to the power 4 is in the hundreds of thousands. So, and there's the final stage is the unity gain that drives the DC blocking cap, and the current is flowing through this meter, which is a 50 microamp sensitivity meter. And this calibration is for setting the full scale, or a certain scale actually, not full scale. In this case it's 0.7 times full scale. And there are other bypass resistances for as you want to change the range. Some of these currents are bypassed so that you don't overrange the meter. So these are resistance used for that, and that is part of the rotary switch that controls a lot of these range functions. So as I mentioned, the low range is below 3 ohms, and there are goes on to 0.001 ohm, 0.003, 0.01, and so on, all the way up to 1K. Now one disadvantage of this machine compared to this guy is that the voltage node here, the return path, is actually grounded. So if you're using this machine can measure resistances in the presence of DC voltages on the when it's in circuit, because it's actually using an AC signal to measure the response. So, and basically it's a tuned amplifier over here at around, the frequency of this is 100 Hertz, so anything that is outside this range will be attenuated severely, and it can actually handle several hundred volts. This instrument, however, has got both floating voltage and current terminals, so it doesn't suffer from that problem. The implementation here is quite different. It's got a phase sensitive meter. It's a lot more complicated, I think, when I looked at the circuit diagram, and it's a lot more expensive as well. It's well known compared to this one. So, but I think in terms of performance, I would think these are very similar, but I haven't compared with this one, the HP. But from what I can see, this has got fairly good accuracy, and I'll show you some results that I will show in my when I do the measurements. So here's the schematic of a different version of this instrument. This unfortunately actually is not the one I have, although this is the clearest schematic in that particular manual that I found, and I'll use this one to just show you roughly the same thing I showed on the board earlier. This is the oscillator portion here, which is made out of regular transistors. This is a NPN transistor, all of them, and the output of the NPN is the AC signal that goes out into this network, which is controlled by the rotary switch that sets the range. So there are 11 settings here, from 0.001 all the way on top to 1K down at the bottom, and the range is split, as you can see over here, with this demarcation where it's broken into the upper and lower range, which is below 3 ohms is over here, and above 3 ohms is on this side. So it bypasses some circuitry when you use the higher range. You don't need that accuracy as well as the gain. So this is the transformer I was talking about that is used in the low range, below 3 ohms, and the input is over here, and the output is to the resistors over here at the bottom. So this loop over here forms the current loop, and there's a voltage sense here, and you can see the bottom, the negative side of the term voltage input is actually grounded to the chassis. So that's the disadvantage of this particular implementation. There's AC coupling here into this amplifier, and This is the 4 stages here, the 6418 miniature, sub-miniature tube. They all are biased by 1.5 volt mercury cell. In my case, I have a D battery, which is slightly higher voltage, but it works. There's another battery over here. Actually, this is the filament battery here, and this is actually a bias for the last 2 stages, and that's also a negative 1.5 volt battery here. This is the plate supply. This is a screen grid which is at 22.5 volts, and the plate is at 35 volts. If I use a 9 volt battery, the actual original battery is a mercury 8.4 volt cell, which you don't get anymore, or very hard to find. So you can actually, this is a vacuum tubes are not going to break down at a few volts above compared to a MOSFET or some regular semiconductor device. They are a lot more rugged and can take a lot higher voltages. Anyway, this is fairly close to what is in the spec, so I think that works, and I tested that. So that's the main amplifier section. The final stage is actually the unity gains output, which is then sent out through here back into this rectification network, 2 diodes and resistances in a bridge formation, where the current then flows into this meter and then exits on the back to the virtual ground on this side over here on the grid of this sub-miniature tube. So these are vacuum tubes, pentodes, and there are five elements in there. Basically the cathode, which is got a filament also on it. Some of these are biased at 0.6 volts, and some of them are biased at 1.3 volts in the original design. So with the 1.5 volt battery, these would be 0.75. In this case, as you can see, there are 2 in series over here, and the 1.5 volt for this one, and some others here. I think this one too. I'm sorry, this is 0.75. There's another this is, I think, the first stage, which is actually located in a different part of the instrument, and these 4 are actually together on the top of the instrument, which is easily visible. Tubes are generally susceptible to microphonics, which is kind of feedback from mechanical vibrations and so on. Hence, this one is actually protected with some sponge and some kind of a soft material. So it's located in a different part of the instrument. Let's see what else I can show you here. So this is actually the tube, the 5 pins which come out and they show a blow up, and all of them have a similar kind of a pin out. These are Raytheon, built by Raytheon in the 1950s and 60s, I believe, and these are still available if you want to get them. So that's this particular part of the circuit is hard to decipher for me. There are a lot of these switches and this arm, the wiper arm, that's hard to trace out. So this, as I mentioned, this is not the schematic for my machine that I have. The one I have is actually, this is another version here. You can see has got even older version, I think. Slightly different. The components are a little bit different. I can see there's a difference in the oscillator circuit. Even there are 2 separate batteries here. Anyway, skipping this one, the actual circuit that I have is this one over here. This one is a bit marked up, so it's even a bit hard to read some of these things because somebody's traced over this, and this has become part of the actual manual that is online right now. But again, this is close to what I showed you earlier, but there are some differences. And in terms of it's got this what I mentioned, the low voltage mode and the high voltage mode. That's why there is this extra set of resistances. Normal voltage mode, this one of these resistors in this string is actually bypassed. So this has got the same number of batteries over here, similar batteries over here, 2 of them, and the batteries for the oscillator. All of these are roughly 1.5 volts. The same meter circuit. There's a slight difference in the calibration part. There is only one calibration resistor, as I showed you in the block diagram. The previous circuit had 2 calibrations, one for the high range and one for the low range. So to simplify things, I went a little bit one step, a little bit less detailed than this one, so I could actually understand what was going on before I could come up with the circuit I showed on the board. And that's this one over here. As you can see, I got rid of some of the extra fluff in terms of all the ranges, and I drew the rotary knob as a rotary knob, so I could actually follow what is actually going on. And so you can see on the left side is the same transformer based input that goes for the low range, and then it goes into the same set of amplifiers, and the output goes back here, and then there's this calibration, and then the rotary switch selects for the low range. It's actually using some bypass resistances, as you can see here, which are different for the low and high range, and the bypass resistance is used for this. Again, you can see that for certain ranges there's a resistance, in the other case it's common over here. It's a common one for all these different positions, so it's much easier to follow over here than on that original schematic over there. And this is the normal voltage and the low voltage implementation using two series resistances. That switch is controlled by this low and normal, off, low and normal, and this off actually is also the power switch, which turns on the oscillator and some other bias circuitry. This high voltage is always on, so it's always powering up this circuit, but being microamps of plate current here, 10 microamps I would say roughly, this doesn't really bleed much power off and can be run for hundreds of hours this way. The actual spec says this meter can last almost 400 hours with these battery setups. So that's the simplified version, and here's the bottom part. Here is the same thing I showed on the board, which is a simplified version of this guy. Instrument over here, it's got a nice case and it can be closed, and the leads over here, which are the measurement leads. This is the current output, and there are two, as you can see, there are two plugs here, jacks, and then similarly for the voltage. Unlike the other Kelvin counts where these are joined together like this is more independent. I like this feature because you can put the current input wherever you want, and then the voltage wherever you want, and close to where the measurement should be taking place. That's some advantage here, and it's really solid, good terminals here. And this is the main knob which sets the range, as you can see over here. I'm not sure if you can see this clearly, but try and zoom in. You can see that goes to 0.001 1 milliohm full scale. That means these fine ticks can be around 30 microohms, but I think down at the bottom of the scale it's got some offset, so I wouldn't worry. I wouldn't trust anything below like 100 microohms or so. So anyway, that goes up to 3. So here's where the upper range starts, 3 on to 3, 10, 30 on the way all to 1K. And in the cal mode you can basically set, once you do in the cal mode, you can when you operate the instrument using this knob here, this will go to 0.7, and that's what the calibration does, set resistance in that feedback parts to get the right voltage. If that is correct, then based on all the other resistances which are accurate resistors in the selector network here, you are likely to get an accurate resistance reading. There's a zeroing function, and then I believe the operator is just when it actually engages the oscillator and turns on everything. As I mentioned, the plate supply, the 30 volts is always there, so you've got to be careful that you don't, it's not going to give you a shock, but if you might accidentally discharge it and get surprised sometimes. These leads fold back into this area here, and that's a nice touch, so everything is self-contained, totally battery operated, unlike the 4328A, which is HP, which can operate both off the mains as well as in battery mode. So I'm going to now, I've removed the back of this one, zoom out again. You can see there are 4 screws which hold this instrument in place. I removed those 4 screws, so I can remove this one here. that's easy to work with actually. So what we have on top is actually the batteries. I'm going to bring the camera closer. So somebody built a jig for this one, putting in the D cells, and then the only specialized battery I would say we need are these two N-type cells, or LR1 cells I believe they're called, 1.5 volts. These drive some bias circuitry, and they're very little current. So maximum current is really from the filament, which is around 20 milliamps to 30 milliamps. And then below this over here are four of these 9 volt batteries here, and they provide the plate voltage and the screen grid voltage for the pentodes. Below down here are the main circuitry for the amplifier path. You can see the four of these tubes, and right here, starting with, this is the first one, second one actually. The first one I mentioned is a different location, so there are 4 gain stages. The final one is actually a gain of 1. These capacitors are the only decoupling caps on this whole network. These handle around 30 volts right across these two, and these 4 transistors over here, let's see, zoom out again. Okay, these are the 2 filter caps, decoupling caps, electrolytics, and these 4 are the oscillator circuitry, the 2 diodes which are in the meter circuit, and the 2 resistors part of the bridge circuit are right here. The AC coupling cap for the meter circuit is here. Very easy to follow the circuit. It's only a single sided board. There are some miscellaneous low value capacitors which are part of the filter network, which has to create this like a band pass filter for this one, for operating at 100 hertz. The 4328A actually runs at 1 kilohertz, so this one is actually better in that sense. It's got less inductive reactance, which can affect the reading of the ohm meter. And below this plate, I'm not going to open this one, is actually that other tube. It's right under this plate over here, and it's got a I'm sorry, you can see below that, it's behind that actually. That's the, if I can shine a light over there, there's actually a tube which is in a box like structure with some sponge like material holding it together with some cushioning effect. The calibration resistor for the range is over here. That only affects the low range mostly. There's also another control I forgot to mention, is this one, which is a symmetry control, which makes the square wave coming out of the oscillator. You can adjust the duty cycle with this one, so it's actually pretty good. From when I measured it, I wouldn't say it's more than a few % off, and that would affect the accuracy, having that off a little bit. So the entire switching network is here. It's pretty complicated. There are 7 stages or leaves in this one, so it's hard to decode this thing. It's hard to check it. But I think all these are very low current resistors, so they nothing to fail actually in this one. The meter is over here, and you can see the transformer is right here, and this is the on-off switch over here for the main on-off, as well as it sets the voltage for low and normal. As you can see here, it's got this indication saying normal and voltage limited mode, and that's about it. And the meter itself is a very nice looking meter with a mirror, very good condition, and it actually sits, you can adjust of course the 0 position when it's off. There is a slight error when you turn it on, but that's probably not an issue for most measurements. So the meter is now on, and I think I got everything in the picture and the video here. It's clearly visible, hopefully everything. Here's a resistor, 2 ohm resistor, which I have measured before, and the meter has been, it's in the normal mode, so it's been put in a larger current, and I'm going to operate it, and you can see now right now it's got this small offset as it, and that's not adjustable, unfortunately. So I kept it on the 3 ohm range. I'm going to show you what happens when I operate it. So as you can see, it's right dead on target, around 2.0 something, just about a little bit above that. And this resistor, I had measured it using my milliohm meter and some other meters at 2.0059 ohms. So I think this reads very well. If I go into the lower voltage limited range, there's a slight error. I think it's okay. When you're using it for certain applications, you're forced to use that, but for most normal operation, it's better to be in this range where it's more accurate. Could probably calibrate that out, but that involves adjusting one of those bypass resistances, which are currently in this design is not programmable like in the other older version of this instrument. So that's the 2 ohm resistor. So this is another resistance box which is quite accurate. This will allow me to do some bigger range tests, and believe me, I've connected it on top over here. You can't see the connections made to the terminals, but just make sure when you use this that you put the current leads on the outside of the voltage input leads, so you measure the resistance right at the terminal. So this is a very good decade box built by General Radio Company, and extremely well designed. And you can see now I'm going to turn on this one again, and this is a 1 ohm. This has got a minimum of 1 ohm and it goes all the way up to 11k or so. You can see this fairly accurate on the 1 ohm scale. And then go to 2 ohms and 3 ohms. So if I go to the next scale, the 10 ohm scale, it's now reading 3 ohms, and then 4, 5, 6, 7, 8, 9 and 10. So I like the linear scale of these ohm meters, much easier to calibrate and check. You can also go into the higher range. Let's go to some much higher range of 300 ohm range. I can set this to back to 0 here, and let's try the 10 ohm range here, or the 100 ohm range. As you can see, this is 100 ohms, 200 ohms, and it's 210, 220, 30, 40, 250. So it's a great instrument for what I paid for it. And one thing I can do with this ohm meter is that I can measure very small resistances well below 1 ohm. And my ohm meter that I built does go down to, practically speaking, maybe 0.1 ohms reasonably accurately. Anything well below that is going to be a problem because of the triboelectric effects which this particular meter gets rid of using this AC signal. That's one of the advantages I forgot to mention. And this can be with this 4-terminal arrangement. Again, it's you can place the terminals, the current and the voltage wherever you want, and gives you some better control over the measurement. So here's a ultimate test as far as I'm concerned, and the type of resistances I want to measure. This is a shunt, as you can see here, for 100 amp shunt, and my ohm meter which I built had difficulty measuring this accurately. It would, depending on how I connected it and how I touched it, because all the triboelectric effects, the connections have to be very perfect. I would see anywhere from 0.1 milliohms all the way up like to 0.12 or 0.13. It would vary, I mean, depending on how I connected it and so on. So that is a limitation of even a milliohm meter that you build. Is you're really looking for absolute value in that neighborhood of 0.1 and below, you really need a very good ohm meter. You may have a resolution of 1 milliohm, but that doesn't mean you can actually measure a 1 milliohm resistor accurately with these type of ohm meters or milliohm meters. This one actually will, and I think it's fairly accurate. Unfortunately, the only way I could check this was to put a large current through it and measure the voltage on it using a regular meter, and that might of course do some heating and so on. But anyway, let's try this one, see what it comes up with. I'm going to the lowest range here, 0.01, 001 that is. And it's 0.74, or is it 750 microohms? I think it's 750 microohms. Yes, 750 microohms is the actual value, and this one is reading around 740 or in that neighborhood. So as you can see, extremely accurate. If I go to this other range, you'll see it drops off quite a bit. I mean, you need a lot more current actually to send into this one. I think the amplifier doesn't have enough sensitivity on that, or may need calibration. But if I go back to the normal operation, it puts a larger current into this thing, and it's got enough gain to show that accurately. So this is the ultimate test for me in terms of measuring tiny resistance below 1 milliohm, and this instrument will do that. So will the other HP, and I've done similar measurements with that, but I haven't compared it head to head with this particular instrument.